exploring heavy industries, advanced factories, and mega-scale infrastructure projects where engineering precision, massive machinery, and innovative technologies drive global industrial progress worldwide. The steelmaking process begins with iron making, where raw materials are prepared and converted into molten iron. Large quantities of coal are delivered to the site and processed in coke ovens, where coal is heated in the absence of oxygen to produce coke. Coke serves as the primary fuel and reducing agent for the blast furnace. At the same time, iron ore from nearby mining operations is supplied in the form of lump ore and pellets, along with fluxes such as limestone to help remove impurities. Inside the blast furnace, coke, iron ore, and fluxes are charged in layers. Superheated air is blown into the furnace, causing the coke to burn and generate intense heat. Through chemical reactions, oxygen is removed from the iron ore, producing molten iron. Impurities combine with fluxes to form slag, which floats on top of the molten iron and is separated. Once the process is complete, the molten iron is tapped from the furnace and transferred to the steelmaking department. The next stage takes place in the basic oxygen steelmaking plant. Here, molten iron is poured into a converter, and high-purity oxygen is blown into the melt. This reduces the carbon content and removes elements such as silicon and other impurities. By carefully controlling this process, different grades of steel can be produced to meet specific requirements. After refining, the molten steel is ready for casting. Casting is carried out in two main facilities. In the billet caster, molten steel is poured into continuous molds and cooled with water until it solidifies. The solid steel is then cut into billets of required lengths. In the slab and bloom caster, the same principle is applied to produce larger sections, such as slabs and blooms. These products gradually solidify through controlled water cooling, ensuring consistent internal structure and quality. After casting, the steel moves to the rolling mill complex. Slabs and blooms are reheated and passed through a series of rollers that progressively shape them into rails, structural sections, and other long products. Billets are also rolled or transported for further processing, where they are transformed into reinforcing steel and other finished forms. Precise rolling and finishing operations ensure correct dimensions, surface quality, and mechanical properties. The final stage is product finishing and dispatch. Finished steel products are straightened, cut, inspected, and prepared for delivery. Through these integrated steps, from iron making and steel refining to casting, rolling, and finishing raw materials, are systematically transformed into high-quality steel products ready for use in construction, transport, and industrial applications. At the Doña Inés de Collahuasi concentrator, copper ore is processed by large crushing, grinding, and flotation machines. These systems reduce ore size, separate valuable minerals, and produce concentrated copper slurry for further metallurgical treatment. Drilling and blasting is the first step in the quarrying process. A blaster carefully lays out the shot pattern so that the correct amount of explosive energy is distributed evenly across the rock face. This controlled layout helps ensure safe blasts while minimizing ground vibration. After the pattern is marked, a subcontract drilling crew drills approximately 50 holes, each about 5.5 inches in diameter, a task that usually takes around 2 days. Once drilling is complete, the holes are loaded with explosives and connected using electronic blasting caps. These caps allow precise timing, so each hole detonates milliseconds apart, improving rock fragmentation and further reducing vibration. After blasting, the broken rock is moved to the next stage, loading and hauling. Material from the muck pile is loaded into two 60-ton haul trucks, using either a large front-end pit loader or a tracked excavator. The loaded trucks then transport the rock over a distance of about 15,500 feet to the primary crushing station. Crushing and screening begin with primary crushing. The haul trucks dump the material into a hopper feeding a 42 by 48 jaw crusher. Before entering the crusher, the rock passes over a grizzly feeder that removes material smaller than 5 inches. The jaw crusher reduces large rocks, typically 3 to 4 feet in size, down to approximately 8 to 12 inches. Crushed material is then conveyed out of the pit and placed into a surge pile, which acts as a buffer and allows the primary crusher to operate efficiently, regardless of downstream activity. From the surge pile, material is conveyed to secondary processing. A vibrating scalping screen separates the rock by size, directing material larger than 3 inches into a cone crusher, which further reduces it to 3 inches and smaller. The output then passes to a triple deck sizing screen that separates the rock into multiple size fractions. Oversized material is routed to a tertiary crusher, while smaller material continues along the processing line. Material between 1 inch and 1/4 inch enters the wash system, where fines are removed and the rock is separated into final product sizes. Water used for washing and dust suppression is recycled within the pit. Finally, processed aggregates are stockpiled, ready for loading and distribution. The laser cutting demonstration begins with the Prima Power Platino Fiber 2D laser cutting machine preparing for operation on the shop floor. The machine is powered up and its control system initializes, checking all axes, drives, and safety systems to ensure stable and precise cutting conditions. Once the system is ready, sheet metal is loaded onto the cutting table, where it is accurately positioned to guarantee consistent cutting quality across the entire surface. Throughout the demonstration, the movement of the cutting head is smooth and precise, reflecting the robust mechanical design of the Platino platform. Linear drives and rigid structural components ensure vibration-free motion, which is essential for maintaining cutting accuracy at both high speeds and high power levels. The machine's ability to transition seamlessly between different materials and thicknesses highlights its flexibility in real production environments. Material handling also plays an important role in the cutting process. Once each cutting cycle is completed, the cut parts are separated from the remaining sheet. Small parts drop through the slats beneath the cutting table, while larger components remain in place for easy removal. This efficient handling reduces downtime between cycles and supports continuous production. The remaining skeleton is cleared, and the next sheet can be loaded quickly, further improving overall productivity. The cutting process starts with thin, galvanized steel sheets with a thickness of 2 millimeters. After the sheet is clamped and aligned, the fiber laser head moves rapidly to the programmed starting position. The 4 kilowatts fiber laser is activated, producing a highly concentrated laser beam that pierces the material almost instantly. Thanks to the optimized piercing technology, the laser creates a clean entry point with minimal spatter. The cutting head then follows the programmed cutting path at high speed, producing smooth edges and precise contours. The efficiency of the fiber laser is clearly visible as thin material is processed quickly while maintaining excellent dimensional accuracy. After completing the galvanized steel cutting cycle, the machine transitions to stainless steel sheets with a thickness of 4 millimeters. The laser parameters are automatically adjusted to suit the different material properties. The cutting head lowers to the optimal focal distance, and the laser pierces the stainless steel with controlled energy delivery. During cutting, assist gas flows through the nozzle to remove molten material from the kerf, ensuring a clean cut and preventing oxidation. The machine maintains steady cutting speed, demonstrating its ability to handle medium-gauge materials with consistent quality and minimal heat-affected zones. The demonstration emphasizes the advantages of fiber laser technology, particularly in terms of energy efficiency and cutting speed. Compared to traditional laser systems, the fiber laser converts electrical energy into laser power more efficiently, resulting in lower operating costs. This efficiency is especially noticeable during the cutting of thin and medium gauge materials, where high-speed cutting significantly reduces production time. The cutting quality observed across all tested materials is consistently high. Edges are smooth, burr-free, and require minimal post-processing. The narrow kerf width ensures material savings, while the precise control of heat input minimizes distortion, even on thinner sheets. These characteristics make the Platino fiber suitable for applications that demand high precision and repeatability. The demonstration continues with mild steel sheets of increasing thickness beginning with 15 millimeters. For this material, the advanced piercing devices play a critical role. The laser performs a carefully controlled piercing cycle to penetrate the thicker plate without causing excessive spatter or surface damage. Once piercing is complete, the cutting head advances along the programmed path at a reduced but optimized speed. The fiber laser maintains stable power output, allowing the machine to produce straight edges and uniform cut surfaces even in mid-thickness mild steel. The reduced cycle time highlights how the Platino fiber improves productivity without compromising quality. As the cutting process progresses, the machine demonstrates its capability on even thicker, mild steel, reaching a thickness of 20 millimeters. The cutting parameters are again automatically adapted by the control system. The piercing phase is executed with precision, gradually penetrating the material layer by layer. This controlled approach ensures reliable piercing while protecting the cutting nozzle and optics. During cutting, the laser beam remains stable, and the cutting head maintains accurate positioning even over longer cutting paths. The result is a clean separation of the thick steel plate with minimal slag and consistent edge quality. Overall, the laser cutting demonstration highlights a streamlined and highly automated process. From material loading and precise piercing to high-quality cutting and efficient part removal, every step is optimized to deliver productivity, flexibility, and consistent results. The Platino fiber proves its capability as a powerful solution for modern sheet metal cutting, capable of handling diverse materials and thicknesses with speed, accuracy, and reliability. The Okuma MU8000VL is a high-performance 5-axis machining center designed for the efficient production of complex, high-precision components such as spiral mandrels and distributor parts. Combining advanced turn milling capabilities with full simultaneous 5-axis control, this machine delivers exceptional accuracy, surface quality, and machining flexibility in a single setup. In the demonstrated process, turn milling is carried out using an indexable R6 end mill with 6 flutes. Programmed via module works, this operation runs at a cutting speed of 105 meters per minute, with a spindle speed of 507 revolutions per minute and a feed rate of 0.7 millimeters per tooth. A shallow axial depth of cut of 0.5 millimeters, combined with a large radial engagement of 50 millimeters, ensures stable material removal while maintaining dimensional precision on the rotating workpiece. For subsequent shaping, 4-axis rotary milling is performed using a E12 Freisa NVDS end mill with 4 flutes. This stage increases productivity through a higher cutting speed of 120 meters per minute and a spindle speed of 3,185 revolutions per minute. With an axial depth of cut of 10 millimeters and radial engagement of 12 millimeters, the MU8000VL demonstrates strong rigidity and smooth axis coordination during continuous rotary machining. The machine's true strength becomes evident during 5-axis undercut roughing. Using the same U12 Freisa NVDS end mill, the process allows plunge angles of up to 30 degrees, enabling efficient access to complex undercut geometries. Precise tool orientation and stable cutting conditions are maintained at identical cutting parameters, highlighting the effectiveness of module works-based NC programming. Root machining and root finishing operations are completed with a U12 Freisa Sphero XR ball end mill featuring 2 flutes. Higher cutting speeds of 152 meters per minute and spindle speeds of 4,034 revolutions per minute are applied, with controlled feed rates and reduced depths of cut to achieve accurate root geometry and superior surface finish. Overall, the Okuma MU8000VL stands out as a versatile and robust 5-axis machining solution capable of integrating multiple machining strategies while ensuring high productivity, precision, and consistent quality. The LIPUS multi-layer spooling system is designed for offshore, mining, lifting, and oceanographic industries, providing unlimited controlled spooling capacity. Its advanced wire rope spooling technology improves safety, ensures even winding, and significantly increases wire rope service life. The Titan Umaro SC is a heavy-duty double-column vertical turret lathe designed for machining large and massive components with high stability and precision. Manufactured in Romania by Umaro, this machine is widely used in industrial environments where oversized cylindrical parts such as sleeves, rings, and housings must be turned accurately. The machine features a robust double-column structure that ensures excellent rigidity during heavy cutting operations. This vertical design allows large workpieces to be mounted securely on the rotating faceplate, while gravity helps maintain stable positioning. Depending on the configuration, the Titan Umaro SC can accommodate various faceplate diameters and large turning heights, making it suitable for a wide range of heavy components. The lathe is typically equipped with vertical tool supports, fitted with multi-position turrets, commonly 5 tool holders, enabling efficient roughing and finishing operations. Some versions also include a side support for additional machining flexibility. The Titan Umaro SC series is available in both conventional and CNC versions, with modernized machines often upgraded with Siemens Cinemeric 840D control systems. Overall, this machine combines strength, adaptability, and precision for demanding large part machining tasks. The process begins when the worker applies a thin, even layer of release agent to the interior surface of the rubber molds. This step is carried out carefully to ensure that all textures and fine details are covered. The release agent reduces surface tension, prevents the concrete from sticking to the mold, and helps achieve a clean and accurate stone surface after demolding. In many cases, the mold is lightly sprayed with water, which further improves material flow and surface finish. Once the molds are prepared, they are arranged on a flat and stable working platform to maintain uniform thickness. At the same time, the concrete mixture is prepared by combining cement, fine aggregates, pigments, and water. The components are mixed thoroughly until a homogeneous consistency is achieved. The mixture must be fluid enough to flow into the detailed textures of the mold, but not too wet, so that the final stone retains strength and sharp definition. After mixing, the concrete is slowly poured into the prepared rubber molds. The worker ensures that the mixture spreads evenly across the entire surface, reaching all corners and recesses. Due to the flexibility and precision of the rubber mold, the concrete naturally conforms to the stone texture without excessive force. Care is taken to avoid trapping air during pouring, as air bubbles could weaken the structure or affect the surface appearance. Once the molds are filled, gentle vibration or tapping is applied. This step helps the concrete settle properly and allows any remaining air bubbles to rise to the surface and escape. The vibration also improves compaction, ensuring consistent density throughout the stone piece. Because the rubber molds are elastic yet dimensionally stable, they absorb vibration without distortion, maintaining accurate geometry. After compaction, the filled molds are left undisturbed for curing. One advantage of using rubber molds is that the concrete mixture can remain inside them for an extended period, even up to several days, without damaging the mold or affecting surface quality. During this curing phase, the concrete gradually hardens as hydration takes place, while the mold maintains precise dimensions and texture definition. As curing progresses, the surface of the artificial stone becomes increasingly rigid. Once sufficient strength is achieved, demolding begins. The worker gently bends and flexes the rubber mold to release the hardened stone. Thanks to the mold's high elasticity, the stone separates easily without cracking, chipping, or surface defects. The mold immediately returns to its original shape after the stone is removed, ready for the next cycle. The demolded stone pieces are then placed on racks or pallets for further curing and drying. At this stage, the stones continue to gain strength and stability. Depending on production requirements, additional finishing steps may follow, such as surface sealing, color enhancement, or edge trimming. These treatments improve durability and enhance the visual resemblance to natural stone. Throughout repeated production cycles, the molds maintain consistent performance. Their resistance to wear, UV exposure, and deformation ensures that surface details remain sharp and dimensions remain accurate. Even after long-term use, the molds do not lose their original form, allowing uniform artificial stone pieces to be produced continuously. This sequence, from applying the release agent, pouring and compacting the concrete, curing and demolding, enables efficient and repeatable production of decorative artificial stone. The process ensures high surface quality, precise texture replication, and reliable results suitable for wall paneling and other architectural applications. Eco Asphalt, developed by Gerhard Herbers, uses a patented reactive binder made from renewable raw materials. It allows asphalt production and paving at much lower temperatures, significantly reducing carbon dioxide emissions, fine dust, energy consumption, and improving worker safety during installation. Conveyor Products and Solutions CPS delivers high-quality conveyor systems and rollers designed to meet the evolving demands of the global mining industry. Today, clients are strongly focused on optimizing production through increased plant reliability, innovative technologies, and a lower total cost of ownership. Reliability and innovation are therefore central to every CPS solution. By building strong partnerships, CPS fully understands client requirements and delivers the right products on time and in full. The company supports operations with safely engineered, efficient, and durable conveyor solutions. Manufactured locally in Australia, CPS products also contribute to the local economy and community. Guided by core pillars of people, zero harm, customer focus, business processes, and growth, CPS continues to scale its production capacity. With proven performance on major projects for leading mining companies, CPS aims to be the preferred partner in the global conveyor industry. The Mohmand Dam project represents a major infrastructure development designed to enhance water storage, flood control, and power generation. The construction site is carefully organized into multiple functional zones to support safe, efficient, and continuous operations throughout the project lifecycle. One of the key early works includes the diversion tunnels and outlet portals, which temporarily reroute river flow, allowing dam construction to proceed in dry conditions. An extensive access tunnel connects critical work areas, improving logistics and the movement of equipment and personnel. The spillway site is strategically developed to safely discharge excess floodwater, protecting the dam's structure and downstream communities. Downstream of the main dam, a re-regulation pond is constructed to stabilize water releases and maintain controlled flow conditions. To ensure smooth access to all construction zones, both right bank and left bank access roads are built, enabling heavy machinery, materials, and workforce to reach the site efficiently. Concrete production is supported by a dedicated batching plant, ensuring a continuous supply of high-quality concrete. The workforce is accommodated in well-planned contractor camps on both the right and left banks, while project coordination is managed through the WAPDA project office and supported by residential facilities in the WAPDA colony. Security and environmental considerations are integral to the project. A 20-kilometer-long security fence, along with a large number of security posts, safeguards personnel, assets, and equipment. At the same time, environmental responsibility is reflected in the plantation of about 1,000 trees, contributing to ecological balance and landscape restoration. Overall, the Mohmand Dam construction showcases a comprehensive approach that integrates engineering excellence, environmental care, and robust site management. The operation begins with sea fastening, which secures all installation equipment and components on the vessel to ensure stability during transport and lifting at sea. Once the vessel reaches the installation location, the pile installation frame, PIF, is lifted from the deck and carefully lowered onto the seabed at the designated pile position. The PIF provides accurate guidance and alignment for driving the foundation pile. After placement, the PIF is leveled horizontally using 4 individually adjustable legs. Each leg is equipped with 1.5-meter extendable mud mats, which distribute the load evenly on the seabed and prevent excessive penetration into soft soil. The mud mats can tolerate a maximum local rotation angle of 3.6 degrees, allowing the frame to adapt to uneven seabed conditions. In addition, the PIF can be installed on a maximum diagonal seabed slope of 2.4 degrees, while still maintaining a level working position. Once the frame is fully level, final checks are carried out to confirm its alignment. Temporary cutting of sea fastening elements is then performed to release the pile and related guiding components. Extendable shims inside the PIF are deployed to guide and center the pile accurately during the initial phase of installation. These shims ensure the pile remains vertical and correctly positioned as piling begins. Before pile driving, the shims are retracted, creating a clear passage so that the hydraulic hammer can pass through the frame without obstruction. The hammer then drives the pile into the seabed to the required depth, forming a stable foundation for the offshore structure. After driving is completed, technicians measure the pile height and check the top of pile elevation. These measurements are critical to ensure the pile meets the strict tolerance requirements for the subsequent jacket installation, which will connect the foundation to the wind turbine structure. Once all measurements are verified and accepted, the pile installation frame is removed from the seabed and lifted back onto the vessel, completing the foundation installation phase and preparing the site for the next construction stage. At Petrofac's Salalah project in Oman, massive tank dome roofs were installed using an innovative air-raising method. The cryogenic, double-walled steel tanks stand 40 meters tall with a 43-meter diameter, one designed for butane and the other for propane. Each dome roof was fully assembled at ground level inside the tank, with the heaviest weighing about 380 tons. By lifting the roofs using air pressure, most erection work was completed at low elevation, significantly reducing safety risks associated with working at height. The process begins with the construction of the foundation slab, which is prepared with projecting reinforcement bars and integrated joint sealing bands. This slab forms the precise base for the prefabricated basement system. Once the foundation is ready, the prefabricated elements are delivered to the construction site in a logical sequence. Access routes must be prepared in advance so that heavy vehicles can reach the assembly area without obstruction. Due to accurate production planning, all wall elements arrive with built-in components already installed. These include door frames, timber formwork sections, electrical conduits, and pipe penetrations. Because these elements are factory integrated under controlled conditions, no additional chasing or correction work is required on site. The installation team positions and aligns each wall element quickly and precisely, ensuring dimensional accuracy and stability. After all wall elements have been erected, the assembly continues room by room with the placement of the prefabricated floor slabs. These element ceilings are laid onto temporary assembly supports to guarantee correct positioning. Balcony slabs or bay window slabs can be produced together with the floor elements and installed at the same time, allowing seamless integration into the structure. Once the floor slabs are in place, the staircase is installed. The prefabricated staircases are available in straight or spiral configurations. They are immediately walkable and suitable for all types of step coverings and surface finishes, enabling safe access during the following construction stages. Next, electrical installers connect and check the pre-installed electrical systems. At the same time, the upper reinforcement layers are placed, and any necessary formwork adjustments are carried out by the site contractor. When all preparatory work has been completed, concreting can begin. concrete is poured into the hollow wall elements, filling them completely. This process creates solid, joint-free reinforced concrete walls with smooth, paint-ready interior surfaces. After the walls have been filled, the final step is the grouting of the prefabricated floor slabs. This completes the structural basement shell, resulting in a stable, high-quality basement structure that is assembled efficiently and accurately while saving both time and construction costs.